Podolsky-Rosen paradox. So, entanglement solves a big problem. The Pauli exclusion principle tells us if we have two particles with spin half, they can't have the exact same state. They're identical particles, so if they have the exact same spin, then their wave function is going to collapse. Which means if one has one certain kind of spin, the other must have a different kind of spin. If one has spin up, the other must have the opposite, spin down. So, I mean, this seems to be a lose-lose situation, right? Because relativity tells us nothing can move faster than light, including information, and that includes measurements from another particle. So here's the thing. If we have two particles, we already know one will be in spin up and one will be in spin down, and they're going to be constantly changing. So without entanglement, if we observe one, then that measurement hits us at the speed of light, which is fine, and we say, oh wow, this one has spin up. But that must mean the other one has spin down, even though we haven't measured the other one yet. So by measuring this, we instantly have a measurement of the other, which isn't possible. We shouldn't be able to get the state of both by just measuring one. And so that's where entanglement comes in. Yes, one of them is in spin up and one of them is in spin down, but you can't know which is in spin up and which is in spin down until you measure both. Their states are entangled with one another, which means you can't know which has upspin and which is downspin. And so that solves the Einstein-Podolsky-Rosen paradox. Entanglement